Entropy. Entropy is a complex concept that isn't easy to understand, but it is crucial to do so as it has had huge implications on the way we live our lives and the direction of civilization, from the way we communicate, utilize energy, and move and function as a society. It was the guiding principle of the Industrial Revolution, sparked the Information Age, and continues to drive current and future innovations in the current unfolding phase in the more virtual world, the blockchain. We begin by revisiting grade school science, where we were acquainted with entropy law, which stipulates that in an open system, energy always flows from a higher concentration to a lower concentration in order to reach thermodynamic equilibrium. What this means in practice is your mug of coffee eventually gets cold, the ice in your beverage melts over time, and that slab of meat in a pan over fire will soon become your delicious meal because energy from the flame transferred to iron molecules but cooled down once the meat was transferred from pan to plate for you to eat. Energy has been distributed to its surrounding area. Entropy is said to be the state of disorder in a given system. Some don't like this definition and prefer to refer to it as the spreading of energy. Energy in a concentrated and usable form is considered ordered, whereas energy in a distributed and unavailable form is considered disordered. Entropy only moves in one direction, toward equilibrium, unless acted upon by a force outside the system. Theoretically, entropy will only rest its steady march once it has brought upon the heat death of the universe, an ultimate end state where there is no free energy. Everything on Earth and in space will eventually expand, explode, die, and distribute free energy evenly through what is really the biggest closed system of all, the universe. In information theory, the entropy of a random variable is the average level of information, surprise, or uncertainty inherent in the variable's possible outcomes, where the fundamental problem of communication is for the receiver to be able to identify what data was generated by the source based on the signal it receives through the channel. In energy, it marches to thermodynamic equilibrium. In information theory, it marches to purity. Communication requires energy, and using energy requires communication. The entropy value of a piece of information provides an absolute limit on the shortest possible average length of a message, or how it can be compressed, without losing information as it is transmitted. Semiconductors, flashlights, and tapping on a pan in Morse code requires human energy, and our communications will always strive for the most efficient means of transmission. In energy, we try to minimize entropy by limiting how much we consume and how efficiently we consume it. Our goal is to find ordered sources of energy and resist the influence of entropy in our bodies. In communication, we minimize entropy by finding information and reducing uncertainty. By reducing disorder via communication, we can halt the entropic process of energy. So, a hunter-gatherer can use language to communicate with another to warn about being eaten by a lion, both reducing the uncertainty of where the lion is, information entropy, and the process of being eaten by a lion, energy entropy. This act of communicating reduces the probability space of all possible events and allows us to act more efficiently and effectively. This is the same principle governing a useful and effective digital, virtual, and the blockchain world, where energy use, transmission, and storage is more obviously intertwined with information creation, reception, and utility and use. Entropy also figures in the economy. Societies take low entropy sources of energy in two forms: stocks and flows. Stocks are things such as rare earth minerals, fossil fuels, and other terrestrial deposits. Flows originate from what are considered renewable sources like wind, water, and solar energy. Here's how much energy we've consumed from 1820 to 2000. The Industrial Revolution shifted the primary energy input of the economy from flows to terrestrial stocks for the first time. Horse-driven plows and wind sails, two forms of work reliant on flows, were replaced by mechanized agriculture and steam-powered vessels, which rely on fossil fuels. We capitalized on the dormant solar energy fossilized over millions of years to free civilization from the restraints of biological earth flows and create breakneck growth in population and GDP. It is important to note the total quantity of energy remains unchanged through the economic process, with the exception of solar. The mining of minerals and consumption of fossil fuels necessary for the production process characterizes a qualitative change that moves energy from order to disorder. Hence, entropy forms the basis of scarcity because humans cannot move energy the other way, from a state of disorder to order, without entropy. It would be physically possible to turn atmospheric carbon dioxide back into a lump of coal. And scarcity is actually a good thing. It's a natural incentive for humans to move and work, to spread from a clumped up inactive state to action and productivity and civilization. But we must also accept the fact we age and degrade. This poses an interesting question today. Is human civilization now showing more physical manifestations of this aging and degrading? Are we moving from civilization to decivilization? Evolution to devolution? The law of entropy will agree. In order to improve communication, we need to manage two things: reduce physical and semantic noise and increase the sender-receiver channel capacity. In addition, to more effectively transmit a message, there should be an appropriate balance between entropy and redundancy. One definition of entropy pertaining to communication is messages which convey highly unpredictable information to the receiver. And redundancy refers to messages which convey highly predictable information to the receiver. When attempting to understand what someone is saying, listeners try to balance the effort required to activate any background knowledge needed to interpret the message. The cognitive benefits of this is straightforward understanding, enjoyment, mental enrichment, stimulation, etc. Typically, listeners seek to invest minimum effort for maximum cognitive effects. If entropy is too high, meaning too many highly unpredictable messages, the effort to decode becomes onerous. The receiver will at best only partially decode or not even decode at all. Thus, the amount of entropy exceeds the receiver's capacity. If redundancy is too high, meaning too many highly predictable messages, there is no required effort to decode. Listeners may expend little interpretative effort and thus may overlook meanings and inferences.
Hot water molecules have more movement than cold water molecules and are therefore more disordered. Ice has even less entropy because of the restricted movement of water molecules in a solid formation.
So how does entropy apply to data science, now a primary feature of the more digital, virtual, and soon blockchain world? Recall that information is resolved uncertainty. The informative value of a communicated message depends on the degree to which the content of the message is surprising. A good example is the use of frequency of letters in language. If the instance of a letter is one event, then the most likely outcome of every given event follows a probability distribution. The more letters there are, the less uncertainty there is in the message. It also depends on the rarity of the letter. Option 1 includes 2 letters with relatively high probabilities, where you can spell out all sorts of words by filling in the missing letter. Option 2 includes the comparatively elusive letter H. Therefore, option 2 communicates more information because it reduces uncertainty to a greater degree. If information is resolved uncertainty, entropy must be the uncertainty needing resolving. The rarity of an event or its surprisal determines its information content. Every time we communicate a piece of information, entropy disorder uncertainty decreases by a proportional amount. Entropy measures the expected amount of information conveyed by identifying the outcome of a random event. Casting a die has a higher entropy than tossing a coin because each outcome of a die toss 1/6 has a smaller probability than landing on heads or tails 1/2. In machine learning, the mathematical interpretation of entropy is used to calculate an information gain metric for many algorithms. At each split, the algorithm selects one attribute to split the sample on and continues to do so until all subsets are pure. Each individual sample in a subset shares the same classification or target value. To measure the purity of a sample subset, the algorithm needs a quantitative measure to objectively choose which feature to split on at every given node. This is where entropy comes in. At each step, the algorithm calculates which attribute will show the highest information gain, then decides on the split. It also computes the expected decrease in uncertainty before and after the split. If it decreases, the split is retained and the algorithm proceeds to the next step. If it hasn't decreased, it has reached purity and it rests.
Imagine 2 machines. They both output messages from an alphabet of A, B, C, or D. Machine 1 generates each symbol randomly. They all occur 25% of the time, while Machine 2 generates symbols according to the following probabilities. Now, which machine is producing more information? Claude Shannon cleverly rephrased the question. If you had to predict the next symbol from each machine, what is the minimum number of yes or no questions you would expect to ask? Let's look at machine 1. The most efficient way is to pose a question which divides the possibilities in half. For example, our first question, we could ask if it is any 2 symbols, such as, is it A or B? Since there is a 50% chance of A or B and a 50% chance of C or D. After getting the answer, we can eliminate half of the possibilities and we will be left with 2 symbols, both equally likely. So we simply pick one, such as, is it A? And after this second question, we will have correctly identified the symbol. So we can say the uncertainty of machine 1 is 2 questions per symbol. Now what about machine 2? As with machine 1, we could ask 2 questions to determine the next symbol. However, this time, the probability of each symbol is different, so we can ask our questions differently. Here, A has a 50% chance of occurring, and all other letters add to 50%. So we could start by asking, is it A? If it is A, we are done. Only one question in this case. Otherwise, we are left with 2 equal outcomes, D or B and C. So we could ask, is it D? If yes, we are done with 2 questions. Otherwise, we have to ask a third question to identify which of the last 2 symbols it is. on average, how many questions do you expect to ask to determine a symbol from machine 2? And this can be explained nicely with an analogy. Let's assume instead we want to build machine 1 and machine 2. And we can generate symbols by bouncing a disk off a peg into one of two equally likely directions. Based on which way it falls, we can generate a symbol. So with machine 1, we need to add a second level, or a second bounce, so that we have 2 bounces, which lead to 4 equally likely outcomes. And based on where the disk lands, we output A, B, C, or D. Now machine 2. In this case, the first bounce leads to either an A, which occurs 50% of the time, or else we lead to a second bounce, which then can either output a D, which occurs 25% of the time, or else it leads to a third bounce, which then leads to either B or C, 12.5% of the time. So now we just take a weighted average as follows. The expected number of bounces is the probability of symbol A times 1 bounce, plus the probability of B times 3 bounces, plus the probability of C times 3 bounces, plus the probability of D times 2 bounces, and this works out to 1.75 bounces. Now notice the connection between yes or no questions and fair bounces. The expected number of questions is equal to the expected number of bounces. So machine 1 requires 2 bounces to generate a symbol, while guessing an unknown symbol requires 2 questions. Machine 2 requires 1.75 bounces. We need to ask 1.75 questions on average. Meaning, if we need to guess 100 symbols from both machines, we can expect to ask 200 questions for machine 1 and 175 questions for machine 2. So this means that machine 2 is producing less information because there is less uncertainty or surprise about its output, and that's it. Claude Shannon calls this measure of average uncertainty entropy, and he uses the letter H to represent it. And the unit of entropy Shannon chooses is based on the uncertainty of a fair coin flip, and he calls this the bit, which is equivalent to a fair bounce. And we can arrive at the same result using our bounce analogy. Entropy, or H, is the summation for each symbol of the probability of that symbol times the number of bounces. Now, the difference is, how do we express number of bounces in a more general way? And as we've seen, number of bounces depends how far down the tree we are. And we can simplify this by saying that the number of bounces equals the logarithm base 2 of the number of outcomes at that level. And the number of outcomes at a level is also based on the probability, where the number of outcomes at a level equals 1 divided by the probability of that outcome. Number of bounces actually equals the logarithm base 2 of 1 over the probability of that symbol, which gives us our final equation. Entropy, or H, is the summation for each symbol of the probability of that symbol times the logarithm base 2 of 1 over the probability of that symbol. And Shannon writes this slightly different, which just inverts the expression inside the logarithm, which causes us to add a negative, though both formulas give the same result. So let's summarize. Entropy is maximum when all outcomes are equally likely. Anytime you move away from equally likely outcomes or introduce predictability, the entropy must go down. Now, the fundamental idea is that if the entropy of an information source drops, that means we can ask fewer questions to guess the outcome. And thanks to Shannon, the bit, which is the unit of entropy, is adopted as our quantitative measure of information, or measure of surprise.
In all of physics, entropy is one of the most unique yet enigmatic concepts, and understandably so. What does it actually mean? The common interpretation is that it is a measure of disorder in the universe, and the second law of thermodynamics states that the entropy can never decrease. In other words, the universe is on an inexorable path to more and more disorder. And it is this one-way property of entropy that some scientists contend is the reason time also flows one way, and that's forward. And if entropy is responsible for something like the flow of time itself, then is it a fundamental property of nature? Or is there something deeper about entropy that really explains what's going on at the core of reality? Scottish physicist James Clerk Maxwell came up with a thought experiment called Maxwell's Demon that showed a mechanism where entropy of a closed system could be reversed. It would violate the second law. It was a paradox that no one could resolve for over 100 years. But when computer researchers at IBM finally did resolve this paradox, they showed that entropy was related to something that could be even more fundamental, and that is information. How is this possible? What is the link between entropy, information, and time? If you observe the rotation of the planets around the sun and then reverse the video, there's nothing about the reversed motion that is unusual. It would be permissible within the laws of physics. Similarly, as far as is known, all physical laws are time reversible. The only laws of physics which appear to be time irreversible is the law of increasing entropy, the second law of thermodynamics. Scrambling an egg, shattering a hard drive, putting sugar in coffee. These are all actions such that if you saw them in reverse, you would immediately know that you're watching something absurd that could not happen. But the second law of thermodynamics appears to be the only law that reversing these processes would violate. Running the movie backward would mean decreasing entropy. The second law states that in an isolated system, the entropy can never decrease. But this doesn't tell us what entropy actually is. So what is entropy? The common definition is that entropy is a measure of the disorder of the system. This is not quite precise. To get a better understanding, let's look at a simple visual example. Let's take a container with gas isolated on one side with a barrier. If we remove the barrier, we expect the gas to expand into the full volume of the container. We have just increased the entropy of the gas. Why is there more disorder if the gas expands into a larger volume? The reason is there is a greater volume and thus more places that individual gas molecules could be. There are more ways to arrange the gas molecules in a larger volume than in a smaller volume. This greater possible number of arrangements is really a better description of entropy. This insight was made by Austrian physicist Ludwig Boltzmann as a definition of entropy, that it is a way of counting the number of arrangements of atoms inside a system. Now, what if we had a plunger on the right wall and pushed the gas back to half the volume of the container? Wouldn't this reduce the entropy back to what it was? No, because compressing the gas like this requires putting work into the system. It would raise the temperature of the gas would heat up, and entropy would increase, making up for any decrease in entropy because of the smaller volume. Why does entropy increase when the temperature increases? Again, this has to do with an increase in the number of ways that the motions of the molecules can be described. An increase in temperature is due to an increase in motions or kinetic energy of the molecules in the gas. As the molecules move faster, the temperature increases, and there are more ways to describe this motion than if the molecules were moving slower. Now, the question is, could the gas spontaneously arrange itself so that it fills only half the volume? You might say, well, that can't happen because it would violate the second law by decreasing the entropy. Yes, it would violate the second law, but the truth is that there's nothing in the laws of physics that really prevents this from happening, except that it is very, very unlikely. The possibility that all the multiple trillions of molecules in the gas could arrange themselves in one side of the container is about 1 to the power 150 billion trillion. This number is so enormous that it is statistically impossible. To give you an idea of the scale, the total number of Planck volumes, the smallest volume that could exist, that would fit in the volume of the known universe is only 10 to the 183. So needless to say, the second law is not going to be violated anytime soon. But it also tells you that the second law is not an absolute law. It is a statistical law. In other words, it could be violated, but it's just extremely unlikely. But in 1867, Scottish physicist James Clerk Maxwell devised a thought experiment that showed that the second law could be violated, and entropy could indeed decrease. And this thought experiment seemed perfectly plausible to scientists, and they could not figure out why it was wrong for over 100 years. British physicist Lord Kelvin later labeled this Maxwell's demon. Imagine a chamber with a divider in the center. If we start out with the gas in one chamber, this gas will distribute itself evenly between the two chambers. Now, what if we put a door between the two chambers that is controlled by a little demon? The door is frictionless, so adds no heat or energy to the enclosed system. The demon controls the door such that he only lets the molecules travel in one direction. When a molecule comes near the door from the right, he opens the door to let the molecule travel to the left chamber. He doesn't let any of the molecules from the left chamber travel over to the right chamber. You can imagine that over time, this demon makes it so that the gas is collected on the left chamber, such that no molecules remain in the right chamber. No work was added and the temperature remained the same, so the entropy decreased. Now, this clearly seems to violate the second law. You might say, well, it's a thought experiment with an imaginary demon. It can't really be done. But you have to remember, this was thought of at a time when the concept of nanorobots and microprocessors didn't exist. It's conceivable that in the near future, we could build a computer-controlled device that could be the mechanical equivalent of the demon. So scientists could not disprove this idea behind this thought experiment for over 100 years. The solution finally came in 1982 by two scientists at, of all places, IBM Research, Rolf Landauer and Charles Bennett. They boiled the idea of the demon down to a fundamental idea behind entropy, and that is information. They showed that in order for the demon to reduce the entropy, he has to gather information about the movement of various molecules to determine when to open and close the door. He's building a memory record. The demon is increasing the amount of information in the system because he is part of the system. This increase in information is an increase in entropy. They showed that the decrease in entropy due to the volume decrease is exactly counterbalanced by an increase in information in the demon's brain. The second law is not violated. You might say, well, all I have to do is erase the memory of the demon. If this was a computer hard drive, we can just reformat the hard drive. And there, now the hard drive has low entropy again. Aha! But Landauer and Bennett showed that erasing information is not free. Erasing information produces heat. It increases entropy. So you can't gather information in the demon and then erase it to reduce the overall entropy. The increase in entropy from the heat of the erasure is perfectly offset by the decrease in information in the hard drive. Now, this is not very much heat, only about 3 billionths of a trillionth of a joule per bit that's erased. But this also gives us a clue about the true nature of entropy, and that nature is that it is really a measure of the information required to express the state of a system. A system with higher entropy requires more information to describe its microstates. When you increase temperature by adding energy, for example, there are more ways that this energy can be shared with the gas molecules. This requires more information to figure out. If we increase the volume, the molecules have more places where they can be, so this requires more information to describe the microstates of the gas. This information requirement is a better definition of entropy than simply disorder. Now, how does time enter into the picture? How is time related to entropy and information? Since all the laws of physics we know appear to be symmetrical with respect to time, there doesn't seem to be any reason time should be asymmetrical, except through the idea of entropy. Entropy is asymmetrical. It flows only in one direction, higher. The feature of the universe that changes with time is entropy. Now, this inspired British scientist Arthur Eddington to postulate that it is the increase in entropy that's responsible for the flow of time. But does time go forward because entropy increases? This is not well understood. It's not a good theory because the prediction it would make is that time should go backward when entropy decreases. There are pockets of decreasing entropy all over the place. The inside of your refrigerator is a place where entropy is decreasing. Your food is getting colder, but time doesn't flow backward inside your refrigerator. Similarly, the Earth at night experiences decreasing entropy, but time does not flow backward at night. So what actually causes time to flow forward? To answer that, let's look at why entropy increases. Entropy increases not because the fundamental laws of physics says it does, but because there are simply more ways that microstates can arrange themselves in the future than in the past. For example, there are more ways to arrange the checker pieces on a checkerboard than when they are neatly arranged at the start of the game. We are much more likely to be in a state of higher entropy than lower entropy as time passes. But since entropy is fundamentally a statistical law based on higher and higher amount of information needed to describe microstates, then could the flow of time also be a statistical phenomenon? That is, time is much more likely to flow forward than to flow backward. If so, this would leave open the idea that time flowing backward is not forbidden, but just statistically impossible. If entropy increases over time, that means that entropy must have been at its lowest possible state at the start of the universe, at the Big Bang. This is sometimes referred to as the past hypothesis, and this low entropy start is thought to be the primary reason why time flows forward. But why was entropy so low at the start? Why did the universe start in a very ordered state? Given all the energy and matter in the universe and all the states that it could have been in, why did it start in this way, in this very small subset of all the different configurations that it could have been in? No one really knows the final answer, but there are some leading ideas. Maybe there's a fundamental reason, but we haven't discovered it yet. And we're trying to explain something that is part of our ignorance. Maybe it's just a fact. It's a property of the universe, like the fundamental constants. Another idea is from physicists like Alan Guth and Sean Carroll. If there's no upper limit to entropy, that is, maybe entropy is infinite, then no matter where the universe started, it would have been in the lowest entropy state. It has nowhere else to go except to a higher entropy state. If time flows forward, as entropy becomes higher, then we are a result of the second law. We are a consequence of the increasing entropy of the universe. If the universe was in thermal equilibrium, we would not exist. The reason we have causality, evolution, biological processes, thoughts, memories, and even consciousness is the second law. Alan Guth points out that if information was not increasing in our brain, we would not have memories or consciousness. This links entropy to consciousness itself. And entropy will continue to increase for billions and probably trillions upon trillions of years when all the galaxies have spread apart, all the stars have been burnt out, dark energy will have ripped apart all matter, including all molecules, atoms, and even subatomic particles. At some point, we will be in thermal equilibrium, at least locally, where we are in the universe. And at this point, entropy may cease its inexorable forward march, and all will become quiet. But space will not go away, and the laws of physics probably won't either. What will remain is the vacuum energy, quantum fluctuations in the fabric of space-time. Given enough time, there will be enough random energy fluctuations within the vast space of the universe that an atom forms spontaneously. A molecule forms spontaneously. Interstellar gases could form. Stars and galaxies could form. The bigger the thing, the longer you have to wait. But if you have an eternity to wait, it will happen at some point. And statistics predict that if you wait long enough, around 10 to the 10 to the 10 to the 120 years, even a universe could form spontaneously.